I want to now switch to transforming models. So I want to talk about transforming rigid bodies. So I will go over, and since I'm changing topics a bit, I will erase here. Transforming rigid bodies. Probably all of you have had some experience in performing transformations to bodies. You may have done translations and rotations before in other subjects that you've studied. What might not be as familiar is thinking about the space of all transformations that could be applied and representing those in some nice way, or performing estimation, designing filters on the space of all transformations. So that's considerably more complex, and my goal is to make that hopefully simple and clear today. So I want to try to explain some of these things about the space of all transformations. In terms of why transform, I want to make some connection back to the last lecture that we have. So why are we performing transformations? Well, it should be clear in the case of movable models. I just talked about that, but there's another case which I think connected very nicely to our lectures from last time, which is perception of stationarity. So that's somewhat counterintuitive. So I need to perform transformations because I need to unmove something that has moved, right? And here's the idea. So I see all of you today in the real world. When I rotate my head, you all move appropriately, right, in the way that I'm familiar with, right. With respect to my head, you're essentially counter rotating in the opposite direction, right. So if I design a virtual reality system, suppose it's a cave-like system or it's a surround sound audio system, it's fixed to the world so that when I turn my head, the stimulus is counter rotating appropriately. Now if I mount the stimulus on my head, if I wear earphones or iPhones, I have a head mounted display, let's say. Now when I rotate my head, the stimulus is unfortunately going to follow it. So if I want to simulate stationarity, if I want to simulate the stimulus being fixed to the outside world, I have to counter rotate, right. Does that make sense? So it confuses people a lot. So you end up applying an inverse transformation to simulate stationarity. We talked about the vestibulo-ocular reflex going back and forth like this, where that's another kind of perception of stationarity, where your body is designed to have your eyes counter rotate with respect to your head. Now we're designing a virtual reality system that's mounted. So when you mount a stimulus to your body, you have to compensate for the transformations that your body is performing. You have to undo those and take that into account, and hopefully do it with very low latency so that your brain does not become confused, right. It becomes unfamiliar input then. So we need to counter rotate the mounted stimulus. More general than counter rotate is inverse transform. And because we have to do that, this requires tracking or filtering, estimation, whatever you like to call it. We need to use sensors and estimate the motion that has occurred of the human body, and then when we figure out what that transformation was, we apply the inverse of it to compensate, to give you, again, this great idea, the perception of stationarity. Does that make sense? So those are two reasons why we're studying transforms today. The first one's somewhat obvious, models are moving in the world, but the second one is a little bit less obvious, is to give you the perception of stationarity, to make you think that the outside world is in fact not moving. Of course, both of these could be happening together and making a big complicated mess. All right. So under transforming rigid bodies, let's imagine transforming each vertex of each triangle. Simple as that. There's going to be three cases that I cover today. Three cases we have the easy case, which is translation. And in that case, I'm going to go over and I'm going to talk about the number of degrees of freedom. So the DOFs in 2D and in 3D. So for translation only, we have 2 degrees of freedom in 2D, and we have 3 degrees of freedom in 3D. And this is really mathematically the easiest case to define, to understand, no problems really. The harder case is going to be rotation, which in 2D is very easy. How many degrees of freedom do we have for 2D rotation? 1. Just 1. And in 3 dimensions we have 3. And this is the part where it gets harder. So things get a little more complicated. It's not hard to apply a rotation matrix and see the result, but it's a lot harder to reason about the space of all 3D rotations. So it ends up getting considerably complicated. I hope to convince you of that and show you some of the kinds of problems, and then help teach you to step around the problems and do things in a nice way so that you do not end up with unfortunate difficulties later. And then the hardest case, which is not too much harder than the 3D rotation, is we put them together. So you get rotation followed by translation. So once I have that, then I can put a rigid body into any configuration that I like, right? I can translate it and I can rotate it, so I can place it anywhere into the world without distorting the body. That'll be a very important property. That's why we write the word rigid here. It means that the body itself does not get distorted. It just gets translated and rotated. Doesn't mean it's rigidly attached to the ground. It just means the body itself is internally rigid. So all distances between pairs of points remain preserved and so forth. There's more than that, but I will get to it soon. So all we do is add the degrees of freedom here. So we get 3 degrees of freedom in 2D and 6 degrees of freedom per rigid body in 3D for 3-dimensional models. So that's the case we're going to be handling, of course, most often, because probably 2-dimensional virtual reality is not very interesting. I have to think about that. All right. So let's start off with the very easy case, just for completeness and consistency, even though this one should be so simple that you might be a bit bored. So translation So suppose we just want to essentially shift the triangle by some amount. I'll write it as x sub t for translation, y sub t for translation, and z sub t for translation. So we want to shift it by some amount. So we just take the coordinates of the triangle. I don't think I want to write out all 3 coordinates. Let's just pick one of the coordinates here, and we'll call it x I, y I, z I. And so if we want to take this point and translate it, then we just apply the following transformation. We take x I, y I, z I, and transform it to x I plus x t, y I plus y t, z I plus z t. Again, very, very simple. We're just performing some translation to it. And of course, here I mean I could mean 1, 2, or 3 if we just number these as 3 different points. x1, y1, z1, x2, y2, z2, and x3, y3, z3, right? So that is the easy case, right? Everybody agrees that's very simple. You should have done that somewhere before. So if that's the case, then the amount of translation that's performed when we move the triangle somewhere else, suppose this triangle gets moved over here after performing the transformation, then the amount of displacement, for example, along the x direction here would be x sub t, right? So that's all we're doing here, just translating it along. Questions about that? Not very much here to talk about.